Hello. Today we're going to look at more ways to show that triangles are similar. First is the side-side-side Similarity Theorem. Now this is exactly like the side-side-side congruence theorem. Remember? We had a theorem back when we were studying congruence which said that if each side of two triangles is congruent, in other words, if all the sides of two triangles are congruent, then the triangles themselves are congruent, which is the same as saying that if all the sides are congruent, then the angles inside must also be congruent. Well, here what we're saying is if the sides are all in the same proportion, AB over RS is the same as AC over RT, and that's the same as BC over ST, then all the angles must also be congruent, and that's the definition of similarity. See, when we've got all the sides in the same ratio, we've got half the definition already. All we have to do is make sure that the angles inside are congruent. Well, that's what this theorem says. It says we can count on it. So as long as the sides are in proportion, we've got two similar triangles. And don't forget, they have to be the same proportion. AB over RS is always going to be a proportion, and AC over RT is always going, AB over RS is always going to be a ratio, and AC over RT is always going to be a ratio. The question is, are the two ratios equal? If that works, then we've got similarity. And here's another theorem which is completely analogous to the one we had for congruence. It's the side-angle-side theorem. And it says that if, remember in congruence, if the two sides in an included angle are all congruent, then the triangles are congruent. In this case, if the two sides are in the same proportion, that is, the ratio of XC to MP is the same as the ratio of XP to MN, and this included angle here, these included angles are congruent, then these two triangles are similar. What if the ratio of this side to this side and this side to this side were the same, and this angle is congruent to this angle? That would be like side-side angle. No, just like in congruence, there is no side-side angle theorem. It won't work. It's not impossible for two triangles which meet that condition to be similar, but there's no guarantee. For the two sides and the included angle, it's guaranteed. They will definitely be similar. Just remember, the way it's written implies the necessity of the included angle being the congruent one. Any of the two angles outside these two? No, that won't imply similarity. Other than that, that's really the most important thing to remember about this theorem. Well, it's too late now. I accidentally left a number in here. You can ignore those. I don't use them. It's the side-angle-side similarity theorem. Depending on what book you use and the order they present them in, the numbers are naturally going to be different. These numbers here, these are not universal. This is not, if you were to go to some other class or some other teacher, some other math professor and say, I use theorem 6-3, I guarantee you he would have no idea what you were talking about. If you said side-angle-side similarity theorem, he would know exactly what you meant. These numbers are different in every single book, so I usually blank them out so as not to add to the confusion. Pretend I blanked it out. Ignore the number, it means nothing. So let's work some problems using these two theorems. These problems will be fairly easy, I think. You probably won't have much trouble understanding them. What about This one here, we got to figure out if JKL or RST, either or neither or both, are similar to triangle ABC. Now we have three theorems so far. We have angle angle, we have side side side, and side angle side. Well, gee whiz, we don't have any angles here. It's going to be hard to prove they're similar using any theorem that involves angles, because we don't know what any of these angles are. So, this seems like the only choice. Side, side, side. So what we can do is check and see if the ratios hold. For instance, ABC and RST, I think we can throw that out right off the bat. Why? Well, the ratio of AB to RT is 16 to 16. That's 1. But the ratio of 14 to 10.5, I'm not sure exactly what it is, but I know it's not 1. And that's all we need. So this is out. This can't be similar to this, because the ratio of this to this is not the same as the ratio of this side to this side. That was an easy one, because if you spotted the 16 on each one, it's really easy to see that these other numbers can't possibly work. For this triangle to be similar, it would actually have to be congruent. These numbers would have to be all the same. You would have a scale factor or similarity ratio of 1. Remember that? Congruent triangles are similar. They just have a similarity ratio equal to 1. So we can toss out RST. It's not similar. But we don't know that either one of them is for sure. So, wait a minute. We got the same thing down here, don't we? This is 20. And this is 20. So the ratio here is 1 to 1. Although, I think I see a possible problem with what I just did. When we check the ratios, we have to match up corresponding sides. This one was oriented the same as this one, so I just assumed that AB corresponds to RT. But now that I look at it, I think that could be an erroneous assumption. So let's try again. We'll do this right this time. Well, we don't have any markings here to show us which angle is which. This looks kind of like a right angle. This one here, this might be a right angle. It's hard to say. Well, we can rely on the authors and assume that they wrote it in the correct order. I think I've shown you before that properly, if you're going to show that the two triangles are similar, you should write them so that the corresponding parts are in the same order. In other words, if vertex J corresponds to vertex R, then you put both of them first and on down the line. If we assume they did that, then we can say that for RST, R corresponds to A, but S corresponds to B. That means AB corresponds to RS, and we need to check the ratio of 12 to 16 against the other ratios. So, I hope you enjoyed watching me make that dumb mistake. Learn from it. Don't make that dumb mistake yourself on the test. Make sure that you're matching up corresponding sides and angles. And don't just assume because they're in the same spot or in the same orientation, like I did, that they're the same. In other words, don't be dumb like me. So we have RS and AB. So what's that? That's 12. We'll just put the small one over the big one. No reason not to, I guess. 12 over 16. Now, what are our next corresponding sides? How about ST and BC? There's ST and BC. So we have 10.5 here and 14 here. Is that the same ratio? 16 3/4, which is 0.75. 10.5 over 14 is also 0.75. And our last ratio would be 16, that's RT, and AC. Here's AC, RT, so it's 16 over 20, and that. So we check our last pair of sides, RT and AC, get 16 over 20, which is 4/5. Oops, that's not 3/4. So we have two sides that are in the same ratio, but the third one isn't. So ABC and RST, nope, they're not similar. They came close, didn't quite make it. Oh, what about JKL? I think I better get rid of all this stuff here. We know this is definitely not similar to this one. And for this one, let's assume they matched them up for us already. So we compare AB to JK. Now here's JK, and here's AB. I guess we'll take the ratio of this to this. That'd be 16 over 20. What about the next ratio? How about BC to KL? Here's BC, here's KL, so that's 14 over 17.5. I'm not putting any relational indicators in here yet. No equality, greater than, less than, not equal to. We don't know what their relationship is yet. I'm just going to write them down and find out. So we got this over this, and it looks like our last one would be JL, that's this here, and AC, that's this one here, or 20 over 25. Well, let's see here. This is 4 over 5, right? This is 4 over 5. So these two are both 0.8. That's easy to see. What about this one? And if your calculator is like mine, each of these came out to 0.8. So JKL and ABC are similar. RST, nope. These two are. And I think I demonstrated that the important part of this problem is recognizing the corresponding parts. It doesn't do any good to match up the wrong sides like I started to do. So make sure you've got the corresponding parts and then check the ratios. And here we have one, another error analysis. Yeah, some dumb guy who makes geometry videos wrote this, but he's wrong. Why is he wrong? Well, let's see here. If we get, remember, we match up correspondences. So AB and PQ should have the same ratio as, say, BC and QR. Well, let's check it. AB is 15. PQ is 24. So we can write that ratio down here. BC is 18. QR is 20. We can put that ratio down here. Uh-oh. As you can see, I evaluated the fraction here as 0.625, and down here it's 0.9. So, not equal. But, wait a minute. Suppose he made a dumb mistake, like didn't put things in the right order. For instance, how about we check the ratio of this side to this side, and then this side to this side? Well, 15 to 20, that's 3/4. I think you can see that pretty easy. Divide the top and the bottom by 5, And up here, divide the top and the bottom by 6, and you still get 3/4. So these two are equal. And in fact, these two triangles are similar. What did he get wrong? Well, he wrote it wrong. 15 to 20 is the same as 18 to 24. So AB over QR. So it looks like he probably should have written this as QRP. Now, or maybe, well, let's check that and see if it works. You got the ratio of AB to QR. Okay. Oh darn, that's not right either. It's R. I could have said QR or RQ. The way my day's been going, naturally I had a 50-50 chance and got it wrong. So A corresponds to R. I think the Q still goes with the B. So if he had written ABC is similar to RQP, he'd be right. It's the only mistake he made. It's important to get these in the corresponding order. Otherwise, when you check similarity, you will find that they aren't similar. So the order, when you're showing similarity, and in fact congruence as well, the order in which you write these does become important. Well, here we need to figure out what this is actually telling us here. What can we conclude given this statement? What is this statement? Well, what they're saying here is that this small little section here and this large section over here, the ratio of this piece to this side is the same as the ratio of this piece to this side. Well, these two are sides of this small triangle here. These two are sides of this large triangle here. So we have two sides that are in the same proportion, the side of this triangle and this side of the large triangle, and then this side of the small triangle and this side of the large triangle, and they're in the same, the ratios are equal, the same proportion. Okay. What about the third side? We could use SSS if we knew this side had the same ratio as this one. Gee, it has some ratio, but we don't know what it is. There's no way to conclude what it would be, since we don't know that this is parallel. If we knew this was parallel, then we would know. Well, if the two triangles were, yeah, they would have to be in the same proportions as the way this is broken up. But that would be a different proportionality. It would be NM over MQ would be the same as this over this. So we don't definitely know that there's a similarity relationship here. There might be. What about angle 1 being congruent to angle 2? Well, if these two lines were parallel, we could say that. But we don't know that they're parallel yet, if they even are. What about 1 and 4? Well, gee, if MN, and MP are congruent, then this is an isosceles triangle, and these two would be congruent. But I don't think anything in the ratios here tell us that these two are congruent. They just tell us the ratios of this to this, and this here to this long one. Well, I don't see any way to show that 1 and 4 are going to be congruent. What about QR and NP? Well, again, if we knew that these angles were equal, then we could use one of our converse theorems. Remember, if the lines are parallel, these two angles are equal. On the other hand, if these two angles are equal, these lines are parallel. But we don't know either one, so we can't say either one. But what about this here? Well, we have the side of this angle, the side of this triangle and the side of the larger triangle are in exactly the same proportion as this triangle to this larger triangle. So if we had an included angle that was congruent, we could use SAS. Well, they both have the same angle here. They share this vertex. And of course, it's congruent to itself. So we have this side similar to this side. This side apart. Yeah, enough if you say similar. The ratio of this side to this side is the same as the ratio of this side to this side, and they share an angle, so it's congruent to itself. So by side angle side, this small triangle is actually congruent to the large triangle. After you know that, we probably could show that they in fact were parallel, and all this other stuff would turn out to be true also. But first, it's SAS that shows us that these two are similar. And that's really a stronger condition than any of these. So. Now here's one where we need to make use of similar triangles to determine various quantities. First we have to do is figure out which triangles are similar. Remember when we got two things crossing like this, two lines that cross? If we can cut them with two parallel lines, we already know that we automatically have two similar triangles. Problem is, how do we know this line and this line are parallel? Well, how about this? PQ is perpendicular to RS. LM is perpendicular to RS. They drew the little right angle symbol in here. Well, we've got two lines perpendicular to the same line. We know from previous sections that means that PQ and LM are parallel. And with parallel lines, we've got all kinds of things that we know are true. For instance, this angle and this angle. These are alternate interior pairs. So this one would be 53. Same as this. On the other hand, this angle and this angle, these two form a vertical pair. So they have to be congruent. Well, there we are. Previous section, we now have our angle-angle theorem. Two of the angles are congruent, therefore the two triangles are similar. And one of the angles they asked for was NQP, which just happens to be right here. So we can write that in right now. And what about this? Well, this is the same as this one here. Again, alternate interior angles. What else did they ask us for? PNQ. Well, they have to add up to 180. So we take 45 and 53, and we subtract that from 180. We added those. Minus 98. So this angle here should be 82 degrees. Let's see here, P and Q. Well, that's the one they asked for up here. 82. What about the length of PQ? Well, where's PQ? Aha, this one here. Well, and for this last one, PQ, we have to remember that everything gets broken up according to the same ratio. For instance, the ratio of this altitude to this altitude would be the same. And the ratio of the section created when this altitude breaks up this segment over here, the ratio of this segment to this segment has to be the same as the ratio of this segment to this segment, or the ratio of this larger segment to this larger segment. In other words, this 12 to 18, that would be the similarity ratio for all the sides. And that's the only one that we do have a ratio for. For instance, this side here, Pn and Mn has the same ratio as Nq and Ln. The problem is we don't have this length to compare to take a ratio of this to this. We don't have this length to take a ratio of this to this. And of course we don't have this length. If we did, the problem would be done. But what we have is the way our altitudes broke up our segments here. Broke up this segment this way and this segment this way. And it has to break them up in the same proportions as in which the sides are in, if that's proper English. So, to make a long story short, the ratio is 12 over 28 over this would be the same as what I'm trying to say is that since they're broken up in exactly the same way, 12 over 28 would be the same as 18 over PQ, whatever that turns out to be. So we've got 12 over 28 18 over x. That gives us that 12x equals 18 times 28. So if we write out those ratios, 12 over 28 equals 18 over x, gives us this stuff. And we can start, say, divide each side by 3, and then divide each side by 2 again. 3 times 14 is 42. So we get that x equals 42, but what was x? Well, that was PQ. That's the quantity we were trying to find. So the answer here is 42. The whole key was in spotting the similarity of these two triangles. And I think I pointed out before, if we just cross two lines and then cut them with two parallel lines, we automatically have two similar triangles. That's always true. Here's one that's going to have to remember our Pythagorean theorem again. We're going to solve for the other two legs here. We're given that we've got two right triangles. I think we don't know that they're similar. They may or may not be similar. I don't think we know yet. And we have this leg is 6, this one's 18, the hypotenuse is 30, this hypotenuse is 10. So, remember Pythagoras' theorem, if we have legs A, B, and hypotenuse C, would be written as A squared. Wow, that's bad. A squared plus B squared equals C squared. But we want the leg. So we're going to have to rearrange this a bit and write that b squared equals, and let's rewrite c as h, so we don't forget this is the hypotenuse, minus a squared. That's the other leg. So what's this here going to be? Well, it's going to be b, the square root of h squared minus a squared, which for this one here would be 10 squared minus 6 squared. And it's 100 minus 36. That's 64, right? And the square root of 64 is 8. So, boom. We've got 8. Well, let's stop for a minute. It's good to spot things with right triangles. Remember in a previous video I mentioned a 3, 4, 5 triangle, and I said that any multiple of those, of that triple, would work. So 3, 4, 5, if we double it, what do we get? 6, 4, 10. So this is your basic 3, 4, 5 right triangle with all the lengths doubled. 6, 8, 10. What about this one? Well, let's find out. I got a feeling this is 6 times 3. This is going to end up being 6 times 4, which is 24. That way this is 6 times 5, that's 30. I got a feeling this is going to be 24 because of our 3, 4, 5 triangle. But let's find out. This unknown side here, I guess maybe we can call it b prime. What's it? Well, it's the square root of 30 squared minus 18 squared. That's going to be the square root of a big number, isn't it? And if we work this out, we get 900 minus 324. We take the square root of that. It turns out to be 24. Son of a gun. So, here we go. The ratio here is 1/3 or 3, depending on which way you're going. 6 to 18, that's 1/3. 8 to 24, that's 1/3. So these two right triangles are similar. And they asked for the ratio of the length. Well, okay, it's 8 over 24, that's 1/3. I think I just said that. Are these triangles similar? Well, definitely. We could use the AAA theorem. We could use the SAS theorem because we know that we had a right angle here in the middle. In other words, so the two included angles, once we know these two are in the proper proportion, these two sides and these two, the right angles are congruent, so we have SAS. And of course, once we computed this side, SSS also shows that they're similar. Now, is this always going to work? Well, that's a fair question. Well, the answer, of course, is yes, they are similar, and it certainly suggests a theorem to me. The question is, the point is, one example does not a theorem make. So, I'm going to see if there's maybe a simple algebraic way we can show that this always turns out to be true. You think maybe there is? Well, let's suppose that these two triangles are now just arbitrary. Wow. If I could speak, I'd be dangerous. Are now arbitrary triangles. Arbitrary right triangles with sides A, B, and H, and A prime, B prime, and H prime. And just forget the numbers that are in there. we're not going to use them. We're going to use the fact that, this is a given fact, that h and h prime are in the same ratio as a and a prime. That's all we know. We've got a right triangle and we've got two legs in the same ratio as the two hypotenuses. Whatever you call them, they're in the same ratio. So what? Does that mean this leg has to be the same? These two, in other words, the remaining two legs have to be in the same ratio? Well, let's suppose our similarity factor is k. In other words, a prime equals k times a. That's the same as saying that a over a prime equals k. That's our similarity ratio, or our scale factor, whichever way you like to look at it. Well, over here, this side b is going to be 8 squared minus a squared. That's the square root of that. Okay, so far so good. What's this side going to be? What's b prime? Okay, let's check it out. Well, same thing, it's h prime squared minus a prime squared, and then we take the square root of that. But what's h prime? K times h. And of course, a prime, k times a. Oh, that looks interesting. What have we got here? We've got a k squared in each term here. So we could write k squared times 8 squared minus a squared. Square root of that. But now we can pull this outside the square root. And we can write k times the square root of 8 squared minus a squared. That's a bad square root. There we go. Well, wait a minute. This looks just like this, doesn't it? So we could write this as k times b. b prime equals k times b. Uh-oh. That means that this leg here is the ratio of this leg to this leg is exactly the same as the other two ratios. We've got the same similarity factor here, KB. So, we're done. We just showed that this leg and this leg are in exactly the same ratio as the other two ratios. So, the hypotenuse leg theorem does exist, and we just proved it. Oh, and, well, that's about it for now.